So good morning, and well, thanks again for the invitation. It's the second time I'm here. I was here in the same meeting 6 years ago, I think it was, for the Space Forum, and it really changed quite a bit how we progressed from that meeting. So hopefully we'll have the same sort of outcome for AVS from today on. So my name is Miguel Carrera. I'm the founder and CEO of AVS. And the idea is to try to challenge these supply chain capabilities, okay? Because we were thinking on when fusion is going to happen, if it's going to be 2035, 2045, 2055, okay? But first, we need to prove the concept. So there are many things to do first. So we need to be alive to prove these concepts in reality. So what are we going to do as supply chain? You need a supply chain for the first phase, which is to demonstrate. Then you need another supply chain from then onwards. You see our motto, vision there, that's boosting scientific knowledge. So what we try to do is to develop tools, instruments, and hardware for scientists to develop their science before, okay? So that was the motto since we started 19 years ago, and that's where we stand right now, okay? Working for the best, make you better, okay? So we try to find difficult problems and try to solve them along with the scientists that are our clients. And in the meantime, if we see something interesting that could be escalated, we invest in that and we develop the full system. So AVS is based in the US, in the UK, in France, and in Spain, and that's, I mean, it's interesting in order to survive. You need to be geopolitically based also, which is important for this sort of projects. And we design and deliver critical systems. The things that we do have never been bought by our client and have never been designed by us previously. Okay, so it's a huge gap between what is expected and what we can do. Okay, so this gap can only be filled by trust. That's the only way to fill this gap. So we do things that are critical, okay, that can, if they don't work well, can perform a critical failure on whatever system. And we do things that work in harsh environments, okay? They have to be precise, have low maintenance or no maintenance at all, and it has to work in cryogenics, ultra-high vacuum, high magnetic fields, and radiation. In order to survive, we need to be present in different sectors, okay? We need to apply this knowledge and this approach to accelerators, to fusion and space. Because as Eric said before, we have peaks and valleys, okay? And we cannot wait for things to happen 20 years. We need to be alive. You need us to be alive whenever fusion happens. In order to do so, we need to respond to different tasks and different areas in these areas that I showed there. So now I will show you some examples in order for you to see the synergies of what we do in other sectors within science that can be applied to fusion technologies. So this is a very good example of turning what was AVS before, which was a subsystem provider for many accelerators in the world, like I don't know, Fermilab, CERN, IFMIF in LIPAC in Japan, etc. And from then on, we decided that there could be an opportunity to develop a full system. Okay, so AVS still does subsystems for others, but if we see an opportunity like this one, we go for it. Okay, this was a thing that we started 10 years ago. Okay, as a concept. So there were things that we know and things that we don't know. So we did the R&D for the things that we didn't know. And it's a very good example of public-private partnership because this is something that is being developed with the help of the CDTI, okay, for a particular customer here in Spain. So this is something that is super interesting for us as a vertical integration. Neutron exploration sources. Here we can train. These are the sort of instruments and things that we can do in a time frame of 18 months to 24 months, and that can train and keep us alive. Okay, in this case, we developed a vacuum vessel and the rotating system for the target at the ESS, at the exploration source in Lund. Synchrotrons, again, in this time frame, 18 months to 24 months, we can train, we can get alive, we can show capabilities on large vacuum vessels, high precision, ultra-vacuum, beryllium, etc., etc. We can show many capabilities. Lasers were mentioned yesterday, and of one of the options. There's a lot of investigations going around laser, high-power lasers, and we have developed a lot of technologies in order to be able to provide this science. As you can see, with the number of flanges in this chamber, you can see how mature is the science. They have a clue of what they're going to get. Okay? Astrophysics, very important, very important. So how all the knowledge that we have on the mirror systems, on how to focus these mirrors, how to mount and dismount these mirrors are critical for some of the diagnostics that we have won for ITER, for example. And critical systems. This is a very, very nice picture that was taken by the Perseverance rover, and that shows specifically two of the subsystems that we did for the Perseverance rover, was the wind sensor for the MEDA instrument and the SuperCam calibration target. And this brought us to the next one. Okay, this brought us this. I mean, this was a very good example of what happened 6 years ago, where AVS was a subsystem level. And at that time, we decided to go farther. We decided to become a prime. And we started off this journey to get to this point, to have our own satellites, and to be a prime in the satellite business. In-orbit servicing. This is something that is going to be a new trend, to have the space as clear as possible. And as you can see here, robotics and remote handling. To be able to master these technologies is absolutely critical. And this can be also applied for the remote handling of ITER. And if we talk about remote handling, there's nothing more remote handling than this, to take samples from the surface of Mars. And we won the contract for the hand that takes the samples for the Mars sample return mission. So remote handling, optics, ultra-high vacuum, cryogenics. Here, cryogenics, this is the Athena instrument. We are going to send to space the largest cryostat ever made for space. And we are developing a lot of technologies, for example, in cryogenic feed-throughs that could be very interesting for the fusion business. Okay? So there are a lot of synergies that we can take over. Things that we see and they can be applied, and we can spill over before fusion happens. So we started off a spin-off company of AVS that is based in the UK, which is called Eurothrusters, that takes all the knowledge from the fusion scientists that we have in-house and brought it to a very specific product for the electric propulsion of spacecrafts in space. So what is about AVS in fusion? Well, we have been working in fusion for the past 15 years, getting more and more responsibilities. Donnes is a very good example of preparation of R&D for many, many years, and now getting to the place in which we can actually try to bid for accelerator. We have been delivering the heating systems for ITER. This is two of the beamline components for the Mythica beam source, you can see there. We are very much into diagnostics. We have been developing a lot of engineering capabilities for diagnostics, CXRS, CPTS, WAPS, radar neutral camera, etc. And we're recently been awarded with wide-angle viewing systems. We are doing the in-vessel viewing systems. So we think that diagnostics is as transversal as it gets, and we could be playing a good part on that. And of course, remote handling. Okay? So these are the things that we believe that we can be of value to the community, of the fusion community in the following years. We will try to invest R&D in these sort of things. So, supply chain. I'm going to take your 2 minutes, okay? So, if it's fine.
Maybe one of them, but
yeah, one of them.
Keep moving.
Okay, so, I mean, if you rely on a wider supply chain. So I have competitors in synchrotrons, I have competitors in neutrons, I have competitors in space, I have competitors in fusion. I mean, we can bring all those to all the different fields, and you will have a wider supply chain. Okay, this is not good for me, but you will have a wider supply chain. Long-term strategic partnerships. You need to be in the long term, because you have to build trust. Because what you're buying, you've never done it, and what you're developing, you have never done it. So trust is key, and strategic partnerships is absolutely key. Even if it's for a vacuum vessel, even for a welding, even if it's for the most simple engineering task, because we have seen many times that many companies are reinventing the wheel in the engineering side. Okay, I'm not talking about the physics side. So you can leverage on the supply chain for the capex. You don't do so many capex. You have this open innovation that comes through all this participation in different fields. So that's also interesting. And these are the questions that I think we could somehow address. So in order to be alive, in order to be there for you when you need it, we need to expand our markets, and there are places to expand our markets. So I think you need to look at other companies in other fields that are trained in this sort of one-off things that you need to receive from the industry. I show you some of the sectors. Maybe there are more: but synchrotrons, neutrons, lasers, actuators, astrophysics, space. All of them can take over many of the challenges that you have. R&D strategies in the fusion case, I mean, I have shown some of the slides, are contracts that I made the quotation in 2014. I got the contract in 2024, and we are going to launch in 2034. So long term is fine, okay, in most of this industry that I can tell you. And then I wanted to raise the question regarding, you were talking about regulation, but it's also a question regarding the QA, PA, the quality on fusion. What is the approach? I mean, ESA right now is trying to reconsider what was their standards, you know, the ECSS, which are the quality standard for space, and trying to tailor them for the new space company. Okay. I agree. I mean, fusion needs their own standard for sure, and if you don't do the things with a standard, whenever you go to be a power plant, you won't be able to be a power plant. So there needs to be a standard, and it's true that RCCM is not the best for fusion. Some of them, yes, but not all of them. And well, that's it from my side. Okay, thank you.